So hey guys, welcome to another video. This time I'm not going to do the let's play. In the last video I uploaded, I talked about something called binary trees in programming. So this is what I'm going to show you right now, what a binary search tree is. So basically a binary search tree is just a tree in which you're searching numbers. And let's say the first number you put is the root node, or the first. Let me just get a bigger picture right now, like this one maybe. Okay. Don't listen to any of these, I'm just showing the tree. Basically this tree is saying I'm going to base myself based on the root node. So the root node is 4, and everything less than 4 is going to the left, and everything more than 4 is going to the right. So is 2 less than 4? Yes, then it's going to the left. Now everything that's less than 4 and less than 2 goes to the left, of course, and everything that's more than 4 and less than 2, and it's less than 2, it's less than 4 and more than 2, goes to the right of 2. So it's basically just how it moves. And this is basically just to optimize search of data, any type of data. In video games, it doesn't necessarily have to be a number. I mean, the number is a reference. So let's say I have 1,000 items. Item number 1, let's say it's my potions. So I'm going to base everything based on my potions. If you're bigger than a potion, then and if your ID is bigger than a potion, let's say 2, then you go to the right. I hope this is a bit this is a bit clear of what I'm saying. I'm still going to make you visualize what I'm saying with binary tree visualization. Look. Let's say I love this. Okay, let's say I want one. Let's say that my weapons are the biggest thing ever. Let's say that's 10. Okay, then 10. I'm going to make my weapons. So we're saying that my weapons are 10. Okay, now. Let's say my potions are less than 1, so I'm going to, and then it's 10 less than 1, then yeah, okay, then it goes to the left. Okay, super. Now let's say my mana potions, those are 2. Now is 2 bigger than 10? No. Then it's 2 bigger than 1? Yes. Then it's going to be going to the right of 1. Now this is a binary search tree. Okay, the problem with a binary search tree is that if I put elements sequentially, it's going to get deeper and deeper and deeper. And for the computer and processing power, making this deeper and deeper and deeper is going to be too heavy on the CPU or the RAM or anything that's actually using the binary search tree. So let's say I put a 9. Let's say I put, I don't know, armor. And now let's say I put an 8. Let's say less armor, like the arm things. Now 7, let's say those are boots. Now you see, I mean, it's getting deeper and deeper. How many elements of depth are there? There's 1 right here, 2, 3, 4, 5, 6, and it's going to get even and even more deeper, and that's heavy for the CPU. Now to solve this problem, there's something called AVLs, or a balanced binary search tree. AVL because it's the names of the people or the person that made this tree. That's why it's called AVL. Let's see, AVL name. Adelson, Belsky, and Landis. Those are who created AVL trees. It's like the HEB or Hewlett-Packard. And so let's do this again. Let's say I want to put each and every element recursively, or sequentially. Now I'm going to get even more deeper and deeper and deeper. Now look what happens. It balanced itself. I don't have a depth of 3 anymore. I have a depth of 2. Now this is what an AVL does. It says I'm going to make each root node have a depth of 2 maximum. If I have more than 2 elements in a root node, then I'm going to balance myself. So let's keep on doing this until we get to 0, or 0. So let's put a 7 and just check what's happening. And if you want to pause, pause. Seven, 6. Now you see, there was a depth of 3 right there. I can have a depth of 3 in the root node because it's my most solid node. It's my less volatile node. So let's continue. 7, 6, 5. And then again. And again. And again. Now, one last time with 0. Now, we have not only a stable tree because it's not too deep, but we also have a stable, it's not too broad also, it's not too big, it's not too wide. How do I know how wide my tree is? Just count how many, like the highest number of nodes you have from left to right. In this case, it's 4. It's 1, 2, 3, and 4. And we count these ones because these two have what we call null leaf nodes, or leaf nodes that don't exist. Each one of these is a leaf node. If you don't have a leaf node below yourself, then you're called a leaf node. If you do have leaf nodes, then you are, I want to say that you are a root. You are just a root node, like a simple root node. Yeah, but you're not like the base root node. Okay? Now, sometimes when you want to balance a tree, even the balancing itself can become heavy. Yeah, because you're not only putting data, you're also saying, if my data is too big, balance. If my data is too big, balance. If my data is too big, balance. And that's also heavy. Now, to make balancing a bit more strict or restrictive, there's something called a red-black tree. Now, have patience with me, because this tree is really confusing and I do not understand it either. But the problem it's solving is I do not want to balance myself too much, and yet I don't want to have too much depth in me. That's basically what's happening. So if you have a piece of paper or want to count how many times this tree is balancing yourself, do it yourself. I'm still gonna count it, but let's see if you see how many times it balances itself. And let's try again sequentially. I'm going to insert. I'm getting a black node, okay? The first node is always a black node. Now I'm going to insert another node, a 9. The next node I'm always going to put after the root node is a red node, okay? Now, let's go again. Now I'm gonna balance myself. When I balance myself, when I balance myself, and if I was a red node, I become a black node. Okay, let's keep on doing this. Okay, if I have null nodes, I do not balance myself, but I become black. This is like having a big black node. Okay. Okay, now I have too many red nodes, so I have to balance myself, but I'm still a black node. Okay, and it's stabilizing. It's saying I don't have to balance myself right now. I know I'm too heavy, I know I'm too deep, but I do not need to balance myself right now. I balance myself and I turn red, and I turn black. Like I said, if I was a red node and I need to balance myself, then I become a black node later. And that's how you do this, basically. And you keep doing it and keep doing it and keep doing it and keep doing it until I get a necessary balancing. Only necessary balances. That's what happens. So yeah. So basically, if we draw this, like if we zoom out and draw this, we're going to basically see this in small. Okay. I don't have paint. How can I not have paint, dude? Either way. Okay, so let's draw this big node. Okay, let's first draw that big node. With this, like this, with this. Yeah. Okay, so this is all of these. Okay, and this is this one. Oh, wait. This is this one. This is this one. We're gonna count this one as null. Okay, since it's a black tree, we're gonna define it as if it was a dead node. And since we have a root right here, we're going to make this, we're going to draw this, okay? We're going to think that when we have red nodes inside a black node, that's inside a red node, then we're going to like basically make you null, okay? But if you do not have any child, I'm going to draw you. You are not dead to me. That's the lesson we're trying to make. So you are not dead to me. So basically this basically this is what is happening. Okay? And in an AVL, this is going to balance itself. When I reach a number that's less than 3. Okay? That's the theory I have. Let's test it out. If I'm wrong, then I'm wrong. If I cannot put another one there. Fuck. No, but either way, my theory is that let's see. Let's put a 2. So I did balance myself. This one balanced itself and it turned black. Okay? That's basically the story. That's basically the lesson I've been trying to teach. Hope it was a bit educating and that you understand a bit more about AVLs and understand a bit why I also like the inside structure of that game. So yeah, I'm going to upload the next video. I don't know if this week. If not, it's going to be next week. But yeah, the next gameplay of 9 Souls is going to come next week. So hope you're ready for that one.